Okay. Right. Okay. So this says so we've got certain curves and surfaces that are given, and we want to find a function for which it's a level set. All right. Find a function for which it's a level set. And by the way, in general, if you want to find a function for which it's a level set, that's not that different from saying we want to just find the equation. Because once you find the equation of the surface, if your equation
just basically use f instead of.
Yeah, if you have something like this, then you take all of that, you throw it over to the other side, and you get stuff minus whatever that stuff was equals to 0, and there's your function. Mm-hmm. Yeah. Yep. Okay. Cool. All right. Okay. So you're asking specifically about these two parts. Let's see here. Now these look like they're related to each other. These are two surfaces obtained by rotating around the x-axis. Well, we have a certain part of the curve, and then we have the entire curve. Okay, so obviously this is a flashback to the rotations of surfaces, they're rotationally symmetric and all that business. So you just kind of have to reverse engineer the surface. And in that section, what we talked about is if you have a surface with a given equation, how to view that as a rotation of a curve, right? And specifically, part of the curve that's in a positive half plane, right? So part 4 here is going to go pretty straightforward. I mean, it's not. We're just literally reverse engineering what we've done before. So let me draw a picture because it's easy to get turned around. But here's our picture, x, y, z, and y equals sine x. Yeah, okay, right. So here's what y equals sine x looks like. Man, my picture is not big enough, of course. Here's what y equals sine x looks like. Now we're interested specifically, though, in the part of that curve with y greater than or equal to 0.
How do we separate that? Do we just label?
Yeah, well, it's going to come about very conveniently, as it turns out. So keep in mind, here's what we know how to do. If we have a surface, if we have an equation for a surface, we know how to identify it if it's rotationally symmetric, and we know how to view it as a rotation of something in a half plane. Well, we're given here, sort of going backwards, we're given that how to view the surface as a rotation of something in a half plane. Right, so this is set up perfectly in some sense, right? Okay, so let's just take a wild stab at this. The idea is that when you're rotating around the x-axis, then it's square root of y squared plus z squared. Square root of y squared plus z squared is, well, in the half plane, it's going to turn into y. Right? So I'm going to take this y here, and I'm going to say, hey, I figure the way to get that to happen is to start with a surface that had square root of y squared plus z squared. Right? So that in mind, let's try this. Let's try square root of y squared plus z squared equals sine x. That's right. And now let's we did this kind of backwards, and so let's try to argue forward and confirm that this is what we hope it is. This is rotationally symmetric around the x-axis. And if I want to understand what is it a rotation of, if I were to say, okay, well, let's look at the part of this curve in this half plane. Well, in that half plane, what I get is, well, that square root on the left becomes y, and then I get y equals sine x, and boom, right? So it works perfectly. Is that cool so far? Yeah. Okay, so number 5 is where it gets a little bit tricky. In number 5...
Oh, so that's the answer?
Well, no, so this is the equation. And then, of course, that means that you got to take this and move it over to the other side, and so you get the square root of y squared plus z squared minus sine x equals 0, and so that's your function. Okay. Yeah. Okay. Yeah? Everybody happy? Okay. So Right. So now we deal with the more awkward version, which is, what if I want my surface? And by the way, let me try to draw this surface that we just generated. I'm going to take an attempt to draw this thing, and it's, you're going to get kind of a little ball-looking thing there, and then a little ball-looking thing there, and that's the surface that we just generated. Part 5 says, that was 4. Part 5 says, I would like to generate all of these balls because I want to rotate the whole sine curve. Right, and forget about this half plane business. That's your problem, not my problem. I want to see all of those. I want to see the whole sine curve rotated around. And the problem is that our tools always insist that we look in a half plane, because if we want to think about the analogous roles of a variable and a radical. The radical's always positive. We can't get around that, right? That means that I've really got to. I have to play the half plane game. Okay, so what we'd like to do then is figure out how can we view this, the surface that you get by rotating the whole curve. How can you view that as a rotation of something that's in the half plane? And so here's my appeal. If I look at this curve, right? If I were to take that blue curve and rotate it around the x-axis, I mean, it is in the half plane. If I were to rotate that around the x-axis, then it generates the same thing that the sine curve does.
And we get that by squaring.
Yeah, well, you got to play the squaring game to sort of think about. So, I mean, here's one way to do that. You could say this blue curve here is y equals absolute value of sine x, right? And that'd be fine. But now you've got absolute values in your equation. Nobody likes that, right? So a cleverer way to do it is to say that, what about this curve? And that's where y is either plus sine x or minus sine x. And another way to write that is y squared is equal to sine squared x. And that's that sort of deals with that absolute value effectively. I mean, this is not the same as saying y equals absolute value of sine x, but it gives us a curve that rotates to make the same surface. Is that cool? Yeah. And so now, same game. Y is replaced by the radical, and so you get y squared plus z squared is equal to sine. Yeah, and then that's right. And then you subtract the other side, you get the function. Yeah. Is everybody good on this one? Just 2 seconds. Everybody happy? Okay, let me stop this recording.